Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 2 lecture. I hope you enjoy it.
This is Chapter 7, Section 4, which is arc length and surfaces of revolution. Alright, so let's start with arc length. And recall the following. The distance formula is the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared, right? And that distance formula is for linear distance, right? The distance along a straight line. So let's see how we're going to use that to figure out the length of an arc, right? An arc length, the length of a curve. So here we go. Let's say that we had some curve, right? And it doesn't matter what it looks like. Let's say it looks like that, all right? And in here, I want to figure out the distance of the curve, or the length of that curve, along there, all the way from A all the way up to B, right? And well, this distance formula, I mean, it doesn't work, right? It doesn't work for this scenario because if I were to use that distance formula here, I would be finding the distance of that line, right? The length of that line, the line between the 2 points. But that's not what we want. We want the length of the curve. So what can we do? Well, what we can do here is we can split up this interval into multiple pieces, right? For example, in here, I'm just going to split it up into these pieces, into 4 pieces. I'll call A x sub 0, x sub 1, x sub 2, x sub 3, x sub 4. Okay. Now, what we can do is, we're going to split this up into these 4 pieces, right? And essentially, we're going to apply the distance formula in each of those pieces separately. So we're going to figure out that distance, then that distance, and then that distance, and then that distance. All right. So perhaps I'll make this a little bit clearer here by exaggerating how far these lines are. Okay. Um, so we can figure out these distances of the straight lines, right? And adding all of those up would essentially be very similar to that curve, all right? And if I were to split up the intervals even more and have more little lines, well, it would be much easier, right? It would be much closer to the actual length of that curve. So essentially, that's how we're gonna apply this distance formula for each of these spots. So let's see what we get here. If I let delta x equal, so delta x of I be equal to x of I minus x sub I minus 1, and I let delta y sub I be y sub I minus y sub I minus 1, right? If I let those values be that, well, then we can get the following. And I'll go back to writing them right. The arc length, the total arc length there, is going to be the sum of, well, from I equals 1 to n, where that's describing all the intervals here. So this is interval 1, interval 2, interval 3, interval 4, right? So we're describing those intervals of, well, the distance formula at each spot, right? So it's going to be the square root of x sub I minus x sub I minus 1 squared plus y sub I minus y sub I minus 1 squared. But we have definitions for both of these. So hold on. So the arc length is approximately, not actually equal to. All right. So what we can say now is, well, this value. Let's manipulate that statement. All right. That square root. So let's see how we can manipulate that. So first, I want to manipulate that inside there. So I have x sub I minus x sub I minus 1 squared plus y sub I minus y sub I minus 1 squared. And this is a minus there. Okay. So in here, well, we already know these definitions for x sub I minus I, x sub I minus x sub I minus 1, so on and so forth, right? So in here, this piece can get replaced by delta x sub I squared, this piece over here by delta y sub I squared. All right, cool. The next thing that we're going to do here is, well, we know that there's two things we can always do to any math problem. And the two things are add 0 or multiply by 1. In this specific case, I want to multiply by 1. And the one that I'm going to multiply is delta x sub I squared over delta x sub I squared. All right. Notice that is just equal to 1. Right. And I'm only multiplying it to this second piece right here, right? Not to this first piece. So what does that give me? Well, what do we end up with? And I'm going to rewrite it a little bit differently. So I'm going to have delta x sub I squared plus delta y sub I over delta x sub I, everything heat squared, times delta x sub I, quantity squared. All right. So that's what we get there. Okay, now, the next thing. I see both of these have a delta x sub I squared. So I'm going to factor that out. So I say, well, if I factor that out, what do I have left here? Well, I'm left with 1 plus delta y sub I over delta x sub I squared. Okay. Now, next thing that I'm going to do here. Well, all of this had that square root sign, right? So let's see what happens when we apply that square root sign. So what we have now is taking the square root, we get the square root of 1 plus delta y sub I over delta x sub I quantity squared times delta x sub I, right, on the outside of this, because all I did was apply the square root to this piece as well, right? Okay. Now, how is that helpful? Well, let's look at this inside here. Delta y sub I over delta x sub I. Let's recall what this really is. The bottom was really x sub I minus x sub I minus 1, right? That was just by definition. And the top by definition was y sub I minus y sub I minus 1. Okay, cool. Now in here, the y values are always tied to the x values, right? And if we were talking here about a function, we would say this would be f of x sub I minus f of x sub I minus 1 over x sub I minus x sub I minus 1. All right, so that's what we have in here. So what do we have so far? All right, so let me step back a little bit. I'm gonna see what we have so far. This entire thing, what we found is now, so let's see. So this statement, we can now say that using stuff that we just found, we can say this is now equal to, well, we still have the summation from I equals 1 to n, but now we've got the square root of, well, what do we have here? We had the square root of 1 plus this thing, so 1 plus this piece became that, f of x sub I minus f of x sub I minus 1 over x sub I minus x sub I minus 1, all of this squared times delta x sub I. All right, cool. Now in here, this was just an approximation for n many intervals, right? Recall that we were breaking up all these intervals, right? But if I start making more intervals here, right? If I start making more intervals and even more, notice what happens in between these distances. these distances are getting smaller and smaller and smaller and smaller and smaller and smaller, right? So essentially, as what we can say now here is, as n, the number of intervals, goes to infinity, that tells us that um, x sub I minus x sub I minus 1 goes to 0, right? Because those intervals were getting smaller and smaller, right? Now, this essentially tells us now that we have s being equal to the limit as n goes to infinity of the summation from I equals 1 to n of the square root of 1 plus, well, we said that as n is going to infinity, this is going to 0, right? And in here, this is essentially the alternate definition of the derivative, right? Recall the alternate definition was f prime of c is equal to f of, let me rewrite that, is equal to the limit as x goes to c of f of x minus f of c over x minus c. So that's the definition I'm talking about here. And since these two, the distance here is going to 0, well, that's the same thing as saying that x minus c is going to 0. So what I can say here now, this is essentially just f prime of x sub I squared delta x. But since we're taking the limit as n goes to infinity, we know that this just becomes an integral. The integral from a to b of the square root of 1 plus f prime of x squared dx. All right, so that's where that comes from. That's the formula. Um, that's the formula for arc length. Now, in here, it doesn't matter. Well, actually, let me just define this. So define definition. So in here, we have to keep in mind that this only happened because we were working with a continuous function, right? So this is for arc length. If we let our function f of x, y equals f of x, represent or be, the y equals f of x be a smooth curve on the interval from a to b, the closed interval a to b. All right. Now it's important that it be smooth because if we had corners, then it wouldn't be differentiable, right? We would have cusps, and we know that functions are not differentiable at corners. So it's important that it be smooth. So the arc length of f between a and b is given by the integral from a to b. So the arc length, lowercase s, is equal to the integral from a to b of the square root of 1 plus f prime of x squared dx. All right. Similarly, so if I'm given, so similarly, if instead of given y equals f of x, if I'm given x equals a function of y, g of y, well, the same exact idea applies, but now we have to have everything in terms of y. So our arc length would be the integral from c to d of the square root of 1 plus g prime of y squared dy. All right, so now we've got the formulas, all right? And in here, it's the same formula. All we need to really consider is what variable we're working with. In other words, what function we're given. So let's start with a simple scenario. Find the arc length. Find the arc length of, or I should say from, find the arc length from the point x sub 1, y sub 1 to x sub 2, y sub 2 on the graph of f of x is equal to mx plus b. All right, find the arc length. Okay, well, let's see what we have. We already know the formula, so we need to make sure that we find the derivative first. So f prime of x is going to be equal to m. Cool. The next thing that we need to do here is, well, we know that the arc length is given by the integral from a to b. In this case, a is x sub 1, b is x sub 2, right? Because it's the bounds of our interval along the x-axis of the square root of 1 plus f prime of x, which in this case is just m squared dx, right? Well, here's the thing. M here is a constant, right? So this square root stuff here is all just one big constant, so it's not even applicable to the integral. So what I'm getting at is, think about it this way. If I have the integral of 4 dx, right? 4 is a constant. The integral of 4 dx would be just 4x, right? But in here, that's essentially what I've got. This entire thing there is a constant. So the same idea is going to apply. So what we're saying here is that this is going to be just the square root of 1 plus m squared. Well, I don't really need those brackets there. I'm going to leave them there because I will need them later. I just realized. All right, times x from x sub 1 to x sub 2. All right, cool. Now let's plug these bounds in there. So I have really plug in the top, plug in the bottom. So I have 1 plus m squared times x sub 2 minus the square root of 1 plus m squared times x sub 1. Both of these have that square root of 1 plus m squared, so I have the square root of 1 plus m squared times x sub 2 minus x sub 1. But in here, m, we know what m is, right? By definition, m is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So what do we get here? Let's see. We have now the square root of 1 plus y sub 2 minus y sub 1 over x sub 2 minus x sub 1 squared. And all of this times x sub 2 minus x sub 1. All right. What else can we do here? In here, common denominator. The common denominator here is x sub 2 minus x sub 1 quantity squared. So x sub 2 minus x sub 1 quantity squared. The second piece is just y sub 2 minus y sub 1 squared. And this first piece, well, I'm going to have to multiply by this denominator. So it's x sub 2 minus x sub 1 squared. And then we have this times x sub 2 minus x sub 1. And now what? Let's see. If I take the square root of the top and the square root of the bottom, I end up with the square root of all this over the square root squared is just itself. And we have this x sub 2 minus x sub 1 out here. Canceling these out, well, what do I get? I get the square root of x sub 2 minus x sub 1 squared minus, plus, right, plus y sub 2 minus y sub 1 squared. And look at that. That should look familiar. That formula right there should look familiar, that statement. Because that's just the distance formula. Now, it should make sense that we just get the distance formula. Why? Because we're working with this function mx plus b. Mx plus b is just a line, right? So the distance between any two given points would just be using the distance formula, right? The square of all that stuff. Which, I mean, is what we got. All right, so that's essentially what this exercise did was it verified that the arc length formula still works even for lines. All right, so let's complicate this. All right, let's complicate this. That was just a very complicated version of coming up with the distance formula again. So now, example B. Let's say I said find the arc length of the graph of this function. F of x equals 3/2 x to the 2/3 on the interval from 1 to 8. All right, so we know what the formula is for the arc length. The arc length is the integral from a to b of the square root of 1 plus f prime of x squared dx. Well, I need the derivative, so let's figure out what the derivative is. F prime of x is equal to just x to the negative 1/3, right? Bring the 2/3 to the front. 3/2 times 2/3 is just 1. Subtract 1 from the exponent, and that's how I get that. So let's see, what do we get here? We have the integral from 1 to 8 of the square root of 1 plus x to the negative 1/3 squared dx. All right, now let's manipulate this expression. In here, negative 1/3 times 2, excuse me, that's 1 plus x to the negative 2/3 dx. Negative 2/3, right? That negative exponent can be brought down to the denominator, so that gives us the integral of 1 plus 1 over x to the 2/3 dx. In there, we can come up with a common denominator, giving us the integral from 1 to 8 of the square root of x to the 2/3 plus 1 over x to the 2/3 dx. All right. At that point, what we can do is take the square root of the top, the square root of the bottom. So what I get now is the integral from 1 to 8 of the square root of x to the 2/3 plus 1 over the square root of x to the 2/3 is just x to the 1/3, right? Recall that square root is the same thing as saying to the power of 1/2, and then 2/3 times 1/2 is 1/3. All right, so at this point, let's see what we can do. I'm going to do a u substitution here. I'm going to let u be equal to x to the 2/3 plus 1, so that du is 2/3 x to the negative 1/3 dx, which really tells me that dx would be, well, multiply by 3, divide by 2, and this divide by x to the negative 1/3, well, divided by a negative exponent, well, it's going to come to the top as x to the 1/3, and this is going to be du, right? Just multiplying everything over. The other thing is, I see that I have bounds in terms of x. I got to change those. When x equals 1, u is, well, 1 to the 2/3 is 1. 1 plus 1 is 2, so u is 2. When x is equal to 8, well, 8 to the 2/3. Well, that's the same thing as saying cube root squared. So the cube root of 8, 2. The cube root of 8 is 2. And then 2 squared is 4. And then 4 plus 1 is 5. So u is 5. So what does that give us now? Well, now we can rewrite this integral, right? This integral is now the integral from 2 to 5, right? Originally it was 1 to 8. The integral of 2 to 5 of this entire thing on the inside, that was my u. So the u to the 1/2 over this x to the 1/3, didn't use it. This dx, well, that's 3/2 times x to the 1/3 du. And at that point, I see that the x to the 1/3 cancels out with x to the 1/3. Awesome. Now, let me just rewrite this before we actually integrate. So we have now 3/2 integral from 2 to 5 of u to the 1/2 du. So at that point, well, we add 1 to the exponent, divide by the new exponent. So I have 3/2 times u to the 3/2, right? Added 1 to the exponent, divide by the new exponent. It's the same as multiplying by the reciprocal, right? So in there we see that the 2's cancel out, the 3's cancel out, and this is evaluated from 2 to 5. So I end up with 5 to the 3/2 minus 2 to the 3/2. All right. We can essentially rewrite this now as 5 radical 5 minus 2 radical 2, right? And here, think about this one right here. 5 to the 3/2 usually means 5 to the 1/2 times 5 to the 1/2 times 5 to the 1/2, right? That's 5 to the 3/2. And these two together are just 5. Similar idea applies with this. So that there would be our final answer. Now, in general, I always want the answer to be in exact form. So you do need to submit it like this: 5 radical 2 minus 2 radical 2. That's the actual final answer that I want. But just to give you an idea of what that is, this is approximately 8.35. All right. But this is my actual answer: 5 radical 5 minus 2 radical 2. So what did we find there? Well, that value, let's see. Let's get the visual for what we just found. This function, our function f of x, was 3 halves times x to the 1/3. Excuse me, to the 2/3. X to the 2/3. And what that looks like is as follows. Right? That's what that function looks like. And what we found here is, if here's 1 and here's 8, we found this curve here. The length of that curve is approximately that, 8.35, which again was 5 radical 5 minus 2 radical 2. Okay. Next one. Let's say that I had the following function. So this is example C now. So C. Let's say that I had y equals ln of sine of x, and we're going to do this from pi over 4 to 3 pi over 4. All right. So the very first thing I need to do here is find the derivative, right? So y prime, and that's going to be 1 over sine of x, and then by the chain rule times the derivative of the inside, the derivative of sine is cosine of x. So I get here cotangent of x, right? So what I get now is, well, I'm going to have that the arc length is the integral. Well, we know the generic formula is the integral from a to b of the square root of 1 plus f prime of x squared dx, which in this case means the integral from pi over 4 to 3 pi over 4 of the square root of 1 plus f prime was cotangent, so f prime squared would be cotangent squared of x dx, right? Now, at that point, 1 plus cotangent squared, you should remember that that is cosecant squared. So pi over 4 to 3 pi over 4 of the square root of cosecant squared theta, not theta, cosecant squared x dx, right? And that's from one of the Pythagorean identities. 1 plus cotangent squared is cosecant squared. And from there, we'll end up with the integral from pi over 4 to 3 pi over 4 of just cosecant of x dx, all right? And at that point, the integral of cosecant is negative ln of the absolute value of cosecant x plus cotangent x. And this is evaluated from pi over 4 to 3 pi over 4, which gives us, well, let's see, plug in 3 pi over 4, the negative ln of cosecant of 3 pi over 4 plus cotangent of 3 pi over 4 minus negative ln of cosecant of pi over 4 plus cotangent of pi over 4. There we go. All right, so let's see what we get here. Cosecant of pi over 4. Well, cosecant is a reciprocal of sine. So we need, and we know what sine of 3 pi over 4 is, right? Sine of 3 pi over 4 is radical 2 over 2. So its reciprocal would be just radical 2. Cotangent of 3 pi over 4. Well, cotangent is cosine over sine, and at that point, cosine of 3 pi over 4 is negative radical 2 over 2, and sine of 3 pi over 4, well, we just said it was radical 2 over 2, so minus 1. Minus negative, plus. And in here, so I end up with ln of the absolute value of cosecant of pi over 4. Well, that's 1 over sine of pi over 4, which again is radical 2 over 2. Well, sine of pi over 4 is radical 2 over 2. So it's reciprocal, it's just radical 2. By the way, if you don't see what I'm talking about with that radical 2 over 2, its reciprocal would be 2 over radical 2. But if I rationalize it, I end up with 2 radical 2 over 2. So it's just radical 2. Okay? For cotangent of pi over 4. Cotangent of pi over 4, well, sine and cosine are the same value there. So cotangent would be the ratio of the two, which would just give us 1. At that point, well, we could combine these two ln's. Notice I have this negative here. So I can say this is ln of the absolute value of 1. Well, let's write it as radical 2 plus 1 over radical 2 minus 1. This is the one that goes on the bottom because of that negative in the front. All right, and that would be my final answer. All right, if we really wanted to, we can rationalize that statement on the inside, but I'll leave it as is. All right. Okay, so next one. Let's say that I have this function, x equals 1/3 times y squared plus 2 to the 3/2. And we're going to go between 0 and 4 along the y values. So here, I mean, it's the same exact idea, right? It's literally the same exact idea, but now we're working with a function of y instead of with a function of x. Okay, but we already knew that the formula doesn't really change. The arc length is the integral from c to d of the square root of 1 plus, and I wrote it as g prime of x, g prime of y squared dy, right? So let's figure out what g prime of y is. Well, if x is g of y, well, I'm going to write it as, so I'm going to say let x be g of y, then g prime of y will be the derivative of this, right? Which would be bring the exponent down. So I have 1/3 times 3/2 times y squared plus 2 to the, subtract the exponent by 1, so to the 1/2, but then by the chain rule times 2y. All right, remember we're doing the derivative with respect to y, so we don't have to worry about this using implicit differentiation because this is the variable that we're taking the derivative of. All right, so now what we can say now is, well, we have the integral now from c to d, so from 0 to 4 of the square root of 1 plus that statement. All right, let's simplify that statement. 3's cancel out, 2's cancel out. So what I really have here is y times y squared plus 2 to the 1/2, right? So now that is what I'm going to get here, right? That's my g prime. So y times y squared plus 2 to the, sorry, y squared plus 2 to the 1/2, and all of this squared dy. All right, so now what do we get here? Let's manipulate this a little bit. Applying that squared, so I have the integral from 0 to 4 of the square root of 1 plus y squared times y squared plus 2, right? Apply the square over here, y squared. Apply the square right here. 1/2 times 2 is 1, so that part goes away. Let's expand this. If I expand this inside here, what do I get? The integral from 0 to 4 of the square root of 1 plus, distribute that y squared, y to the 4th plus 2y squared dy. But let's look at that. That statement, I can write it as y to the 4th plus 2y squared plus 1. Notice that this factors out to be y squared plus 1 quantity squared. So what we can do now is we can say we get the integral from 0 to 4 of the square root of y squared plus 1 squared dy. At that point, the square and the square cancel each other out. So all we really have here is the integral from 0 to 4 of y squared plus 1 dy. And if I go ahead and integrate, well, what do I end up with? I end up with y cubed over 3 plus y evaluated from 0 to 4. Plug in the 4, so I end up with 4 cubed over 3 plus 4. minus plug in the 0. Well, 0 minus 0. Exciting stuff there. So now, 4 to the third. Well, what is 4 to the third? 4 to the third is 4 times 4 times 4, which is 64. And we have that plus 4. Recall that 4 in terms of thirds is 12 thirds, right? And 64 plus 12 gives us 76. So I end up with 76 thirds. All right. So there we go. That's the arc length, 76 thirds for that function from 0 to 4. All right. All right. Let's kick it up a notch though. E. Let's say that I have f of x being ln of x, and here we're gonna go from the interval from 1 to 5. All right. And again, we're looking there for the arc length along that. All right. So, well, what's f prime of x? F prime of x is 1 over x. And we know what the integral is supposed to be for the arc length. The integral from a to b of the square root of 1 plus f prime of x squared dx. All right. So plugging these things in here, I end up with the integral from 1 to 5 of the square root of 1 plus f prime is 1 over x. So 1 over x quantity squared dx. All right. All right, I'm just going to go ahead and write this differently. I'm going to say we have the integral from 1 to 5 of, in here, this 1 over x quantity squared is really just 1 over x squared, right? So what I'm going to do is I'm going to come up with a common denominator. So I have the square root of, the common denominator is going to be x squared. This second numerator, well, that's just 1, right? But this first numerator is going to become x squared. And I've got that dx. Now that I've got that common denominator, I can rewrite this as the integral from 1 to 5 of the square root of x squared plus 1 over x dx. All right. Now, at this point, well, what should we do? This, at first glance, might look like it's a u-sub problem to you, but it is not. It's not a u substitution. All right. Why is it not a u substitution? Well, let's say if I let u be equal to x squared plus 1, then du is equal to x dx. The problem is that we don't have this x dx anywhere up here. We don't have that extra x on top, right? So in other words, this is not going to cancel out. But what we can do here is we can do trig substitution, right? We can apply some trig substitution on this. So if I let x be equal to tan theta, right? Because here I have function squared plus constant squared. If I let x equal to tan theta, then dx would be equal to secant squared theta d theta. We'll worry about the bounds afterwards. In fact, I'm going to return this back into terms of x later. So let's just look at that integral. So we have now the integral of, let me write that a little bit lower. The integral of the square root of tan squared theta plus 1, right? X was tan theta, so x squared is tan squared, over tan theta dx. And dx here is secant squared theta d theta. So now in here, what we can do is we can replace some of these things, right? Tan squared plus 1. Tan squared plus 1 is secant squared. So here I have the square root of secant squared theta, all of this over tan theta times secant squared theta d theta. But then the square root of secant squared is just secant, and then secant times secant squared is secant cubed. So let's see what we get here. We have integral of secant cubed theta over tan theta d theta. All right, let's look at this statement. And I'm going to look at that separately just so that we don't get lost with all the extra integrals. In here, secant cubed theta over tan theta. So secant cubed theta over tan theta will be the same thing as saying secant cubed theta times cotangent theta, right? So dividing by something is multiplying by its reciprocal. From here, secant cubed, that's really 1 over cosine squared. This will be 1 over cosine cubed theta. And then cotangent is really cosine theta over sine theta. So in here, this cosine cancels out one of these. That becomes 2. And we end up with just 1 over cosine squared theta and times 1 over sine theta, right? And at that point, well, that's really saying 1 over cosine squared is really, not cosecant, sorry, secant squared theta. And then we have that times cosecant theta. But we know that secant squared theta is really tan squared theta plus 1. And then we have this times cosecant theta, right? And if I distribute that cosecant theta, well, I end up with tan squared theta times cosecant theta plus cosecant theta. And if I rewrite this tan squared and cosecant theta, well, what do I really have? Tan squared is really sine squared over cosine squared, right? Sine squared theta over cosine squared theta. And then this cosecant squared was 1 over sine theta. And then we still have this plus cosecant theta. We'll leave that out there. And in here, this sign cancels out one of these. So I really have here, and I write it as sine theta over cosine theta times 1 over cosine theta, right? I split this cosine squared into cosine times cosine. And I have times cosecant theta plus cosecant theta. And sine over cosine is tangent. 1 over cosine is secant. So I'm going to write it as secant theta tan theta plus cosecant theta. All right. So that was this statement, right? The secant cubed over tan theta. So what do we get now? Well, we get the integral of this now. Secant theta tan theta plus cosecant theta d theta. But the integral of secant theta tan theta is just secant theta, right? Because the derivative of secant is secant tangent. So the integral of secant tangent would just be secant. And then the integral of cosecant is negative ln of the absolute value of cosecant theta plus cotangent theta, right? Technically plus c, but we're about to change all these values, right? Because the problem wasn't about theta, it was about x, and x was equal to tan theta. So if x is equal to tan theta, well then what do we get? We get, here's theta from SOHCAHTOA, opposite adjacent, right? So opposite adjacent, giving us that the hypotenuse is 1 plus x squared square rooted, right? And at that point, let's see, what do we have? We have a secant theta. So from here, secant theta, secant is a reciprocal of cosine. Cosine is ca adjacent over hypotenuse. So I have hypotenuse over adjacent. But over 1, we don't really write. All right. Minus ln of the absolute value of cosecant. Cosecant is a reciprocal of sine. Sine is opposite over hypotenuse, so I get hypotenuse over the opposite. The square root of 1 plus x squared over x plus cotangent. Cotangent is a reciprocal of tangent from SOHCAHTOA. Tangent is opposite over adjacent, so I have adjacent over opposite. And both not plus c anymore, right? Because now that I have it back into terms of x, I can apply my bounds. And my bounds were from 1 to 5. All right, so we're going to evaluate all of this from 1 to 5. So let's go ahead and do so. Before I do that, actually, look at this statement right here. I'm just going to rewrite it as follows. So I have 1 plus x squared minus ln of the absolute value of the square root of 1 plus x squared plus 1 everything over x. All right, because I had a common denominator, I can combine those two into being the same fraction. All right, so now what does that give me now? Well, what I end up with now is, well, plug in 1. Plug in 5, plug in the top, right? 5 squared, 25. 25 plus 1, 26. So I end up with the square root of 26 minus plug in 5. Well, radical 1 plus x squared, we already know what that is. It was radical 26. So I have radical 26 plus 1 over 5 and perhaps I should have done that first one in square bracket, minus, plug in 1. 1 squared, 1. 1 plus 1, 2. So I end up with the square root of 2 minus ln of, and really here this should be an absolute value, just like this one over here, these two should have been. Ln of, well, this part is just radical 2, and we have that plus 1 over, over 1, right? I'm just plugging in this one. All right, so I mean, in here, we can really write this final answer as follows, and I'm going to group them a little bit. So I have really radical 26 minus radical 2 minus ln of, well, in here, these are all positive, so we don't really have to use the absolute value there. So we can say radical 26 plus 1 over 5. And then we have, I already applied the radical 2 over here, so minus negative means plus ln of radical 2 plus 1. And I'll leave it as that. All right. Now, if you want to get an idea of approximately what this is approximately 4.3675. All right. And visually speaking, what did we find? Well, our function was ln of x. And that's what ln of x looks like, right? And what we did was we found the from 1, from this point, that's at 1, to 5, to this point, we found the length of that curve. So I'll color it that way. We found the length of that, right? All right, so that was a lot of stuff on arc length. Now let's talk about the next thing on this one, which is surface of a revolution. All right, so area of a surface of revolution. Area of a surface of revolution. All right, so in here, let's take what we're talking about. So here's our definition. When the graph of a continuous function is revolved about a line, the resulting surface is a surface of revolution. All right. So essentially, what am I saying? Let's say that I had here this line, right? And I'm rotating about this line over here. So if I rotate that graph around this line, well, what do I get? Well, let's do the following. Let's just copy and paste this so it looks way more accurate. We end up with that and something like this, right? And we end up with that. All right, so in here, notice that we're using the statement the surface, right? Ooh, that's not what I meant to do. What's going on here? Sorry about that, guys. All right, technical difficulties. So what was I doing? All right, so in here, we were rotating this about this axis, and I'm talking about the surface of it, right? I keep saying the word surface here. We're only considering the surface of this shape. We're not considering all the space inside there, right? So that's what's different here about these revolutions, these rotations, versus what we had already been doing. In the previous section where we did rotations or revolutions like this, we were considering all the space being filled in. And here, all we're looking at is this sheet on the outside, the actual surface of this, right? for the surface area. So this is what we get here. I'm not going to actually derive this formula. The idea here is that we're just taking this one little line and adding up all of the little lines that would come up throughout this entire rotation, right? All of those little lines are all going to be added, and in the background too, right? All those little lines on that. So in here, let's get our formula. So the definition here for the area definition is area of surface of a revolution of a surface of revolution. Spelling is hard. All right, there we go. Ooh, didn't mean to cross it off. All right, so if we let y be some function of x, right? And so we're going to let that y be a function of x, and we want it to have a continuous derivative on the interval, on the closed interval ab, right? So that also implies that y has to be continuous on that interval, all right? The area S, and notice here I'm going to be using a capital S, of the surface of revolution is formed by revolving the graph of f about a horizontal axis, a horizontal or vertical axis, is the following. S is equal to the integral from a to b of r of x times the square root. Sorry, I missed something out here. 2 pi. 2 pi times the integral from a to b of r of x times 1 plus f prime of x squared dx. All right. Essentially here, this should remind you of a formula that we worked with in the past, in the previous section, right? This should remind you of the volume of revolution, right? 2 pi radius height. So the shell method, this should remind you of the shell method, right? And here, essentially what we're doing is we're just taking that last thinnest shell for this without all the inside stuff. All right. And in here, where r of x is the distance between the graph of f and the axis of revolution. All right. Similarly, if we were given a function of y, it doesn't matter what we're doing. Then, oh, so hold on. Before I give you the function of y stuff, notice here that I said horizontal or vertical axis. So whether we're rotating about a horizontal or a vertical axis, it doesn't matter. It's still the same formula if I'm given a function of x. All right. If I'm given a function of y, it's very similar. It just ends up being 2 pi integral from c to d of r of y times the square root of 1 plus, so I'm saying, so if given, if x equals g of y, so I'll use g prime of y here. All right, g prime of y squared, dy. All right. Now in here, I do want to mention something here real quick. In general, I'll make a note here. So note, if ds is equal to the square root of 1 plus the quantity of f prime of x squared dx, then the arc length here, s, is just the 2 pi integral from, not the arc length, sorry, the surface area here is 2 pi integral from a to b of r of x ds, our radius function times this statement. All right. That I just want to mention because this version comes up in other like in things like physics, or and also like if you end up moving to Calc 3, you might see statements like this where we just write ds like that. All right. But in general, I mean, we know what it is. All right. So now let's do some examples here. All right. So example F. Let's say that I said that we've got this function f of x is equal to 1/3 x to the third, and we're going to do this from 0 to 3, and we're going to revolve about the x-axis. All right. So in here, well, it doesn't really matter what axis we're rotating about, right? We know the formula is still the same. The surface area is 2 pi times the integral from a to b of r of x times the square root of 1 plus f prime of x squared dx. All right, so let's see how to apply this. In here, let's get a visual to what we're doing here. We're doing this. So we have this function 1/3 of x cubed, and that essentially looks something like this. All right. And in here, we're saying, well, the region from from 0 to 3, from 0 to 3, let's say that's 3. This region, this piece is what we're rotating about this way, but only this line, right? Only this curve. That's the only piece that we're rotating because we're taking the surface only. So what is the radius here? Well, the radius to this axis of revolution would be that distance, right? So let's see what we get here. We're going to get now that s is equal to 2 pi times the integral from 0 to 3 of our radius function, in this case, the actual f of x, right? Just that distance right there, because this is our function. So we have x cubed over 3 times the square root of 1 plus the derivative squared. And what was the derivative of this? Well, if I look at f prime of x, the derivative would be just x squared, right? So here I have x squared. So what do I get here? I get 2 pi integral, well, I'll put this 3 out here. So 2/3 pi integral between 0 to 3, from 0 to 3, of x cubed times the square root of 1 plus x to the fourth dx. In here, we can do a u substitution. Let's say that u is equal to 1 plus x to the fourth, then du would be equal to 4x cubed dx. And look at that, I have an x cubed dx right there. So really, du over 4 is x cubed dx. And that's what we're going to use to replace that. But look at our bounds. Our bounds here are in terms of x. I need them in terms of u. When x equals 0, u equals 1, right? 0 to the fourth, 0. 0 plus 1, 1. When x equals 3, u equals 82, right? 3 to the fourth is 81, right? 3 times 3 is 9, and then that times 9 is 81. 81 plus 1 is 82. All right. So now, in here, what do we get? We get this 2 pi over 3 is still out here. 2 pi over 3. This integral from 0 to 3, well, now it's from 1 to 82. This x cubed dx, that's going to be my du over 4. And this 1 plus x to the fourth, that's our u. So we have u to the 1/2. All right, this 2 and this 4 reduce, right? If I pull this 4 out here, they reduce. So I really have pi over 6, right? Because the 4 becomes a 2. Pi over 6 integral from 1 to 82 of u to the 1/2 du. And what does that give me? Well, that gives me u to the 3/2, or pi over 6 times u to the 3/2, but then divided by 3/2 means multiplying by the reciprocal, so there's our 2/3, and this is evaluated from 1 to 82, and well, what does that give us? It gives us pi over 6 times, well, actually, that 2/3 and that 6 becomes just a 1/9. So I have 1/9 times 82 to the 3/2 minus pi over 9 times, plug in the 1 to the 3/2. And if we really wanted to here, well, I can just write this as pi over 9 times 82 radical 2 minus 1. 82 radical 82, sorry, not radical 2. 82 radical 82 minus 1. Whatever that is, all right? And that would be the surface area of what happens when we rotate this, right? And well, what would that look like? Well, hopefully you can now have this idea on your own that this would look like this, right? That's essentially what that looks like. All right, cool. Let's do another one. So that was F. G. Let's say I had the function f of x is equal to the square root of 4 minus x squared, and we're going to do this from -1 to 1. And we're going to rotate. We'll do about the x-axis again. All right. So the very first thing I need to do here is I know I'm gonna need to figure out what f prime of x is. So f prime is 1/2 times 4 minus x squared to the -1/2, and then by the chain rule times -2x. So what I can say here is really just, well, these twos cancel out. So I have -x over 4 minus x squared to the 1/2. All right. So now let's see what we get here. We need to do the surface area, and the surface area is 2 pi integral from a to b, so that's -1 to 1, of our radius function. So let's get a visual here. Let's figure out what our radius function is. So this function, well, that's a semicircle. That's a semicircle of radius 2. All right? That's a semicircle of radius 2. So in here, in this semicircle, we're working from -1 to 1. So we're figuring out here's -1, here's 1. And this is the piece that we're going to be rotating about the x-axis. Well, what would that look like? Well, essentially it looks like this. And perhaps I'll do it in blue. So it looks like this, right? That's rotated this way, right? All right. So in there, what's my actual radius? My radius function is just this distance from here to there, which happens to be the actual function, right? And we have what the value of the function is. Excuse me, what the definition of the function is. So that's our radius. So in here, well, what are we going to do? We're going to say that our surface area is going to be 2 pi, the integral from -1 to 1 of our radius function, which we just said was the square root of 4 minus x squared, times the square root of 1 plus f prime of x, which was that stuff over there, -x over 4 minus, well, let me make more space here. So in here, plus, we just said it was -x over the square root of 4 minus x squared, and all of this squared, right? That to the power of 1/2 is just that square root there. All right, and all of this dx. All right, and again here, what I'm doing was r of x times the square root of 1 plus f prime of x squared. All right, so let's see what we can do. All right, we need to do a lot of manipulation here. Let's start by looking at just this piece right here. So I have the square root of 1 plus negative x over the square root of 4 minus x squared squared. What does that give me? Well, applying that squared, I end up with the square root of 1 plus x squared over the square root. Well, that square is actually gone, right? Square rooted, that's gone. So I have 4 minus x squared. Common denominator, square root of something over 4 minus x squared. So that's going to be 4 minus x squared plus x squared, right? Now at that point, well, what do we get? We get on top, the negative x squared and the positive x squared cancel each other out. So I just have 4. On the bottom, I have 4 minus x squared. Taking the square root of the top and bottom, I end up with radical 2 over radical 4 minus x squared, right? And so that was just this piece right here. So what we get now is that our integral is now, well, 2 pi from negative 1 to 1, 2 pi integral from negative 1 to 1 of radical 4 minus x squared, radical 4 minus x squared, times, well, this statement, right, and this entire thing. And that entire thing, we just found that became this little thing, this little fraction over here. Radical 2 over radical 4 minus x squared dx. So these radicals cancel each other out. So I can pull that radical 2 all the way out here. So I have 2 radical 2 pi integral from negative 1 to 1 of 1 dx. And the integral of 1 is just x. So I end up here with 2 radical 2 pi x evaluated from negative 1 to 1. So it's 2 radical 2 pi times 1 minus 2 radical pi times negative 1, which overall minus negative means plus. So I really get here 4 radical 2 times pi. All right. And I just realized I made a mistake. Real quick, it's an easy fix. The square root of 4 is not square root of 2, it's just 2. So that's just 2. So that's just, ooh. So this piece, this radical is gone. So that's really 2 times 2. And the 2 times 2 is 4. Let's fix all of that. All right, so let's fix the rest of that. 2 times 2, we just said it's 4. So we have here 4 pi x. All right, so 4 pi times 1 minus 4 pi times negative 1. All right, minus negative is plus. I mean, the idea was still the same, but now I end up with the correct answer of 8 pi. All right, let's do one where everything is in terms of, but what's given to us is, we're going to do this about the y-axis, is what I was trying to say. So let's do this about the y-axis. Example H. So in here, I'm going to have y equals cube root of x plus 2. And we're going to say let x be between 1 and 8. And we're going to do this about the y-axis. And in here, recall that the formula was the same whether we were doing a vertical or horizontal axis, right? The only really thing that we care about is was the function given in terms of x or in terms of y. So because it's given in terms of x, we're going to do everything in terms of x. So let's see, what does this function look like? Well, the cube root function plus 2 looks something like this. All right. And what we're doing here is we're rotating the region between 1 and 8. So let's say here's 1 and here's 8. And we're taking this piece between 1 and 8. We're taking that piece and we're rotating it this way, right? But what does that do for us? Well, now let's think about what the radius is. At any given point, the radius is this distance, right? And that distance in general, we can call it x, right? That distance in general is just x. So now we can say, well, our arc length is going to be 2 pi times the integral of our radius function. In this case, our radius function is just x. So x from 1 to 8 of the square root of 1 plus f prime squared. All right, so let's take the derivative of this. Y prime would be 1/3 x to the negative 2/3, right? I just looked at the cube root as to the power of 1/3 and took the derivative. So that's what I get here. 1/3 x to the negative 2/3. All right. And then dx. Let's look at that statement in the inside though. Let's simplify that, or let's rewrite that. So I have the square root of 1 plus 1/3 x to the negative 2/3 squared. All right. Applying that squared. So I have 1 plus x to the negative 4/3 over 9. Bring that negative exponent to the bottom. 1 plus 1 over 9x to the 4/3. Come up with a common denominator. The square root of 9x to the 4/3 plus 1 over 9x to the 4/3. Take the radical at the top and the radical at the bottom. So the square root of the top, square root of 9x to the 4/3 plus 1. Square root of the bottom, well, square root of 9 is 3. The square root of x to the 4/3 is x to the 2/3. All right. So what did we find so far? That was just this piece, right? So what we can do now is we can rewrite this integral now, and we can say that this integral becomes 2 pi times the integral from 1 to 8 of x times this fraction, 9x to the 4/3 plus 1 over 3x to the 2/3 dx. All right. So let's see, what can we do there? This 3, pull it on the outside, so we have 2 pi over 3, integral from 1 to 8. This x to the first and x to the 2/3 on bottom gives me x to the 1/3 on top, right? 1 minus 2/3 is positive 1/3. And in here we still have a 9x to the 4/3 plus 1 dx. All right. Next thing I'm going to do here is let's do a u substitution. Let u be equal to 9x to the 4/3 plus 1. Then du would be, well, bring the exponent down, so we have 9 times 4/3 x to the 1/3 dx. Now this 9 and this 3 reduce, so really what we have here is du is equal to 12 x to the 1/3 dx. But look at that, x to the 1/3 dx, x to the 1/3 dx. So what we can really say here now is that du over 12 is x to the 1/3 dx. All right, let's change our bounds. When x equals 1, 1 to the 4/3, 1. 1 times 9, 9. 9 plus 1 is 10. So when x equals 1, u is 10. When x equals 8, 8 to the 4/3. Well, that's really saying 8 to the 1/3 to the 4th. And 8 to the 1/3 is 2. 2 to the 4th, 16. 16 times 9. 16 times 9 so is 144, right? 9 times 10 is 90. 9 times 6 is 54. 90 plus 54 is 144. But then 144 plus 1 is 145. So u equals 145. So, all right. So what does this integral become now? Well, we have this over 12 out here, right? Well, let's see. We got 2 pi over 3 integral from originally 1 to 8. Now it's 10 to 145. And this x to the 1/3 dx, that's our du over 12. And this radical stuff, the inside of that radical, is just our u, right? So in here, bringing out that over 12 all the way out here, I end up with, well, the 2 and the 12 reduce. The 12 becomes a 6. 6 times 3, 18. So I have 18. Integral from 10 to 145 of u to the 1/2 du. And the integral of u to the 1/2 is u to the 3/2 times 2/3. And all of this evaluated from 10 to 145. At that point, well, the 2 reduces with the 18. That becomes a 9. 9 times 3 is 27. So I have pi over 27 times, plug in 145. 145 to the 3/2 minus pi over 27 times, plug in 10. 10 to the 3/2. Right? If we really wanted to, we can rewrite this now as pi over 27 times 145 radical 145 minus 10 radical 10. All right, and then whatever that is the final answer. I mean, that's the final answer. It's some positive number there. All right, I'm gonna end the video there. All right, that concludes 7.4, which again was arc length and surfaces of revolution.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.